Good morning to everyone. I am Sweta from GMRP Cultural. So, in this video lesson, I am going to discuss about the need for microwave tubes, list various microwave tubes, explain the working of multi-cavity Klystron amplifiers, and list the applications of multi-cavity Klystron. So, first of all, we will discuss the need for microwave tubes. Okay. So, first of all, the microwave frequency range will start from 300 megahertz, that is 0.3 gigahertz, but the spectrum space between 0 to 30 megahertz is absolutely full. That's why the frequency range is greater than 1 gigahertz is called as a microwave frequency range. Okay. So the conventional tubes such as triodes, tetrodes, pentodes, etc. can be used as amplifiers and oscillators more efficiently. So, but these conventional tubes cannot be used as an amplifiers or oscillators at high frequencies. So, here we are using a microwave frequency range is greater than 100 megahertz. That is, as the microwave frequency range starts from 300 megahertz, that is 0.3 gigahertz. So because at higher frequencies the output drops off. So for that reason, in the year of 1960s, microwave communication had almost replaced 40% of telephone communication between major cities of the world. Okay, so the factors contributing to a reduction of output at UHF or circuit reactance, in that inter-electrode capacitance and lead capacitance, transmit time effects, cathode emission and plate heat dissipation area, power loss due to skin effect, radiation and dielectric loss, gain bandwidth, product. So microwave tubes, here the microwave tubes performs the same function of generation and amplification in the microwave portion of the frequency spectrum that vacuum tubes perform at lower frequencies, but high frequencies we use microwave tubes. The microwave tubes was developed when the use of frequency spectrum went beyond 1000 megahertz into the microwave range. The microwave tubes uses a transit time in the conversion of DC power to radio frequency power. So the interchange of power is accomplished by using the principle of electron velocity modulation and low loss resonant cavities in the microwave tube. Okay, so this is about need for microwave tubes. Coming to the list various microwave tubes. So they are basically, we have two types of microwave tubes. First one is linear type or O type tubes. One more is crosser type or M type tubes. So linear type or O type tubes, here the electron beam travels the length of the tube and is parallel to the electric field. So in this case, both velocity and density modulation will take place, creating the bunding effect. So it is also called as linear beam tube, linear type or linear beam tube or O type tubes are further divided into following categories, that is Klystrons, traveling wave tubes. So Klystrons it is a two cavity oscillators, reflex Klystrons, multi-cavity amplifiers and extended interaction oscillators are there. in traveling wave tubes, helix, BWO and coupled cavities are there. Next, cornicatrans. Next one is crossed field or M-type tubes. Crossed field or M-type tubes. Here a principal feature of such tubes is that the electrons travel in a curved path. Okay, so that's why we call it as a crossed or M-type tubes. These are crossed field devices where the focusing field is perpendicular to the accelerating electric field. Again, these are divided into magnetrons, crossed field amplifiers and calcinotrons. Okay, so in the first of all we will discuss about the multi-cavity Klystron amplifier. So first the construction of multi-cavity Klystron amplifier will discuss. So this is the diagram of multi-cavity Klystron amplifier. Here the multi-cavity Klystron amplifier consists of a glass envelope. Okay, it consists of a glass envelope in which there is an electron gun. Okay, it is a glass envelope. It consists of an electron gun. So see here, this arrow mark shows the electron gun that is composed of heater and cathode. Okay, so it is composed of, here we have a heater and cathode. Okay, so after the electron gun, we have two focusing electrodes. Okay, so here we have a cathode and heater. Here we have a two electrodes, focusing electrodes. So because of this, focusing electrodes function is to keep the electron beam in the center. So here the electron beam has to be centered. We have to keep these focusing electrodes. Okay, so at the end there is a anode. So one see here we have a another one, that is an anode is kept at a positive potential. So which is to be kept at a positive potential with respect to the cathode and is used to attract the electrons emitted from the cathode. So the function of anode is to attract the electrons emitted from the cathode. Okay, so next, whenever a high velocity electron beam is, one see here, whenever a high velocity electron beam is from the cathode is produced, focused and sent down along a glass tube through an input cavity, that is a buncher, a field free drift space and an output cavity, that is a catcher, to a collector electrode or anode. Okay, so the input and outputs are taken from the tubes via resonant cavities. Okay, the bunching process is in a two cavity Klystron is not perfect since large number of electrons which are out of phase arriving at a catcher cavity between the bunches. Therefore, the maximum gain of 20 dB can be achieved. So, to obtain the higher or more than two cavities, here we are using more than two cavities are employed practically. So, this arrangement is called as a multi-cavity Klystron amplifier. Okay, so here we are using. So here this is the construction of multi-cavity Klystron amplifier. Okay, so here the multi-cavity Klystron amplifier consists of a glass envelope in which there is an electron gun that is composed of heater and cathode. One see here it has an electron gun that is composed of the heater and cathode. So after the electron gun, we have two focusing electrodes used to keep the electron beam in the center around the glass envelope. So there are two cavities. So here there are two cavities known as buncher and catcher cavity. This is the buncher cavity and catcher cavity. The buncher cavity is input cavity, catcher cavity is an output cavity. Between the cavities around the glass envelope, magnet is used. Here we are using a magnet used in order to keep the electron beam in the center. Okay, at the end there is an anode that is kept at a positive potential with respect to cathode and is used to attract the electrons emitted from the cathode. A high velocity electron beam is from the cathode is produced and sent down along a glass through an input cavity, a field free drift space and an output cavity that is a catcher to electrode or anode. The input and output cavities are taken from the tube via resonant cavities. So here we are using only two cavity cluster, that is not perfect, only it produces only 20 dB gain only. So to obtain a higher gain we have to use more cavities. So this arrangement is called as a multi-cavity cluster amplifier. So coming to the working, so whenever the switch is on, the electrons, starts emitting from the cathode. So from the cathode the electrons will be starts, that forms the electron beam. Because of this electron beam will be formed. So this high velocity electron beam is focused and moves at a uniform speed towards the collector, that is an anode electrode, so which is at a high potential with respect to the cathode. Okay, so with respect to cathode it has a high potential. The beam passes the gap A in the buncher cavity and RF input signal to be amplified is applied to the buncher cavity with the help of the loop coupling. As a result, the bunch of electrons will be formed near the buncher cavity and reaches other cavities with highly excited. It is then allotted to drift freely without any influence from RF fields until it reaches the gap B in the catcher cavity. Due to its strong field strength, the excitation of electrons takes place and we will get an amplified output from the catcher cavity. If the number cavities increases, the gain of the multi-cavity cluster is also increases. The beam is then collected by the collector electrode. Similarly, an early electron that is EE, so that is EE that passes the gap A slightly before the reference electron ER is subjected to a maximum negative field. Hence, this early electron is declared and travels with a reduced velocity V0. This electron EE falls back and reference electron ER catches up with the early electron. So as a result, these actions, the electrons in the bunching limit gradually bunch together as they travel down the drift space from gap A to B. The pulsating stream of electrons passes through the B and excite the oscillations in the output cavity. So here the bunching occurs only once per cycle, centered the reference electron with a proper design. A little RF power applied to the buncher cavity results in a large beam current at the catcher cavity with a considerable power gain. So this is all about the working of multi-cavity Keystone amplifier. So coming to the applications of multi-cavity Keystones used in TV transmitters, used in satellite earth stations, used as a power amplifiers at a 6 GHz and used in radar transmitters. So this is all about multi-cavity Keystone amplifier.